At hypersonic speeds, air stops behaving like air.
Imagine flying faster than a bullet, shattering speed records at Mach 5+.
But how do you build an engine that won't melt or disintegrate under that immense pressure?
We're about to unveil the mind-bending materials and microscopic precision forging
that make hypersonic flight a reality.
Let's begin.
The nickel-based superalloy billet is heated to 1150 degrees Celsius to make it deformable without melting. Then, approximately 3,000 tons of force compress the billet to realign its internal grain structure.
Next, the billet is removed at 150 degrees Celsius to prevent uneven cooling and internal stress. This compression elongates the grains to increase fatigue resistance.
The aligned grain structure allows the alloy to withstand extreme thermal and mechanical loads. After forging, the alloy is cooled under controlled conditions to prevent internal cracking.
The component is reheated to 980 degrees Celsius to refine its microstructure. Rapid cooling locks the grain structure in place to increase strength. The alloy is tempered at 700 degrees Celsius to reduce brittleness while maintaining strength. Excess material is removed to prepare the component for precision machining.
Computer-controlled machining shapes the component to exact dimensional tolerances.
Each surface is measured to tolerances as tight as DQ 0.01 millimeters.
Ultrasonic testing is performed to detect internal defects that cannot be seen on the surface of the metal. Surface inspection is carried out to ensure that no micro cracks remain after machining.
Only components that pass all structural and dimensional inspections are approved for engine assembly.
Engine assembly begins by positioning the forged and machined core components within a controlled cleanroom environment to prevent contamination. The combustion chamber liner is aligned precisely inside the outer casing to ensure even heat distribution during operation.
Structural bolts are tightened to 450 millimeters to secure the chamber while maintaining correct stress distribution.
Each injector nozzle is manufactured with microscopic precision to ensure uniform fuel-air mixing at high velocity.
The internal airflow channel is aligned precisely to maintain stable supersonic airflow through the combustion section.
A thermal barrier coating is applied to protect the chamber walls from temperatures exceeding 1500 degrees Celsius during hypersonic operation.
The coating forms a ceramic layer that reduces heat transfer to the structural metal beneath it. High-temperature pressure sensors are installed to monitor combustion stability during engine testing. Each sensor is calibrated to ensure accurate pressure readings under extreme operating conditions. Thermocouples are positioned near critical areas to measure temperature during combustion.
These sensors allow engineers to verify that internal temperatures remain within safe design limits.
The reinforced intake structure is installed to withstand intense air compression at Mach 5. The intake geometry is designed to compress incoming air without causing flow instability.
The assembled engine core is mounted on a test stand to prepare for structural verification.
Structural verification is carried out to confirm that all mechanical joints meet specified torque requirements.
Fuel lines are pressurized to detect leaks before high-temperature operation.
Stable pressure readings confirm that the system can withstand operational fuel delivery loads. A controlled fuel flow test verifies uniform distribution through the injector system. A cold airflow test is conducted to confirm stable supersonic flow through the combustion channel. The engine is secured to a reinforced ground test stand designed to contain extreme thermal and mechanical loads. High-pressure air systems are connected to simulate the airflow conditions experienced at Mach 5.
Fuel supply lines are connected and pressurized to ensure stable delivery during ignition.
Engineers monitor live temperature and pressure data to verify safe ignition parameters.
Ignition is initiated to begin controlled old supersonic combustion inside the chamber.
Sustained combustion confirms that the fuel-air mixture remains stable under high-speed flow conditions. During operation, internal temperatures can exceed 1500 degrees Celsius, placing extreme stress on structural materials.
Vibration sensors measure structural stability to detect early signs of mechanical failure.
Stable data readings confirm that the engine is operating within its designed performance limits.
After shutdown, the engine is cooled gradually to prevent thermal shock and structural stress.
The engine is placed inside a high-enthalpy wind tunnel to simulate airflow conditions equivalent to Mach 5. Compressed and heated air is accelerated toward the intake to replicate real hypersonic flight conditions. The intake compresses the airflow to increase pressure before it enters the combustion chamber. Airflow stability is monitored to ensure combustion can remain controlled at high velocity. Sensor data is analyzed to verify that airflow velocity and pressure remain within design parameters.
Fuel is injected into the compressed airflow to confirm stable combustion under simulated Mach 5 conditions.
Thermal data is monitored to ensure chamber walls withstand temperatures exceeding 1500 degrees Celsius.
Structural expansion is measured to verify that thermal growth remains within calculated limits. Vibration analysis confirms that structural oscillations remain below critical failure thresholds. Engine performance data is compared against simulation models to validate design accuracy. The engine is operated for extended durations to evaluate sustained thermal and structural stability.
Repeated thermal cycling is conducted to assess resistance to material fatigue. Post-test material analysis verifies that no microcracks have developed within the alloy.
Pressure cycling tests confirm that structural components withstand repeated load variations.
Fatigue data is analyzed to ensure the engine meets long-term operational life requirements. After endurance testing, the engine undergoes final structural inspection to verify physical integrity. Ultrasonic inspection is repeated to confirm that no internal damage developed during high-temperature testing. Dimensional verification ensures that thermal expansion has not altered critical tolerances. Engine performance results are reviewed to confirm compliance with design specifications. Upon successful validation, the engine is cleared for integration into the aircraft platform. The validated engine is positioned beneath the aircraft fuselage for structural integration. Mounting brackets are aligned to transfer aerodynamic and propulsion loads safely into the airframe. Fuel delivery systems are connected to integrate the engine with the aircraft's onboard supply network. Electrical and sensor systems are connected to allow real-time monitoring during flight. Integrated system diagnostics are performed to confirm communication between the engine and aircraft avionics.
Cockpit instruments are verified to display accurate real-time engine data.
A restrained ground run is conducted to validate stable engine operation while the aircraft remains stationary.
Airflow behavior around the airframe is observed to detect any aerodynamic disturbances. Ground test telemetry is reviewed to confirm that engine performance matches laboratory validation results.
Taxi testing verifies steering control and engine responsiveness before takeoff. Throttle response is gradually increased to confirm stable airflow and combustion at higher power settings.
During the takeoff roll, engine output is monitored to ensure consistent thrust generation.
After liftoff, engine parameters are closely monitored as the aircraft transitions to climb. Initial climb validates stable engine operation under increasing altitude and airflow conditions.
The aircraft accelerates through subsonic speed, while engine performance remains continuously monitored.
As the aircraft passes Mach 1, airflow compressibility effects are carefully observed. During supersonic acceleration, intake compression efficiency is evaluated to maintain stable airflow. The intake system compresses incoming air without mechanical compressors to prepare for hypersonic combustion. As the aircraft approaches Mach 5, aerodynamic heating increases significantly along the leading surfaces. Fuel and air remain precisely mixed to sustain stable combustion at extreme velocity. Thermal loads increase dramatically as aerodynamic heating intensifies across the airframe.
Flight telemetry confirms that temperature, pressure, and velocity remain within calculated design limits.
Sustained hypersonic cruise demonstrates that the engine performs reliably under real operational conditions.
Every stage of this engine, from forged alloy to flight integration, is engineered to survive extreme conditions.
Its reliability begins at the microscopic level within the material itself.
Its performance depends on precise airflow compression and controlled supersonic combustion.
Its endurance is proven through repeated testing under sustained thermal and structural stress. Hypersonic flight is not defined by speed alone, but by the precision engineering that makes sustained operation possible.